Swayam Prabha. Digital India. Educated India.
Welcome to module 6, lecture 2. We will continue with strength of concrete, aggregate contribution. Also, we will look at some other contribution. So, if general outline of this discussion should be paste aggregate bond, where we will talk about paste strength, then water cement ratio, surface roughness, chemical composition, etcetera, related to the aggregate. Then effect of aggregate properties, but we will also look a little bit on air entrainment, compaction and age, and lastly we will look just introduce the tensile strength of concrete. So, in the last lecture actually we looked into the effect of essentially how strength is controlled or governed by water to cement ratio, compressive strength of concrete of is or cube compressive strength. We measure in terms of cube or cylinder compressive strength, and that is essentially governed by water cement ratio as a major factor. The other factors, some of the other factors will come to light today. First is paste aggregate bond, all right, paste to aggregate bond. As we said that concrete is a particulate system, particulate system like this, aggregates and aggregates etcetera, all kind of aggregates you will have, and they are bonded by paste system, paste aggregate system. So, this bond is very important, and yesterday we talked about, we said that aggregate paste interface, this plays a very strong role. So, therefore, one has to look into how what governs the paste aggregate bond. So, let us just have a look at that and how it affects the concrete strength. So, we can look into that, and to do that one can look into this kind of a diagram which shows, say figure this one shows, diagram 1 shows, if you have different cement, the flexural strength of paste would be something like this. Flexural strength of paste will be something like this. Flexural strength of paste. 2 shows strength of paste aggregate bond. 2 shows strength of paste aggregate bond. So, this is the paste aggregate bond. So, then 3 is the ratio of bond to paste strength. Ratio of bond to paste strength. So, this is this side, right hand side is the ratio. These are the strength in MPa, these are the strength in MPa, and this is the curve for ratio. So, for example, here this strength, flexural strength of the paste and strength of paste aggregate bond, and this is the ratio of bond to paste strength. So, this divided by this. Now, you can see this value is somewhere here. When it comes to this increases because this is lower, this reduces, but not as much as this. Here it will still be low, and here basically the ratio, this is quite low, this is low. So, ratio is also somewhere there, but here this increases, this also reduced. So, this ratio increased. So, you can see the ratio varies, it is not a constant line. In other words, paste strength, bond strength, paste strength do not directly govern or 100% govern the bond strength. If had it been the case, for example, if I increase the strength of the paste itself, flexural strength, let us say in this particular case, or in a way a measure of tensile strength, let us say, then strength of paste aggregate bond, this strength of paste aggregate bond, had this ratio, it would been solely dependent on flexural strength of the paste or strength of the paste itself, then I would have got a constant line, but I am not getting a constant line. it means there are other factors which governs. So, strength of paste aggregate bond is not only controlled by strength of the paste, not necessarily controlled by the strength of the paste. Where strength of the paste is higher, bond strength is here, where in this case strength of the paste is much lower, but the bond strength is not that much low. So, this ratio actually increases. Had it been all same, it would have possibly increased, and if you see here, paste strength is quite low, but bond strength is quite high, it is as high as this. So, this value has increased, the ratio has increased significantly. So, bond strength is a function of the paste strength, all right, but this is, I mean, it is not a constant. It is not necessary that you increase the paste strength, bond strength will increase. Okay. So, that is the first point. So, bond strength may not increase, may increase or may not increase. So, bond strength is lower than that of the paste, that of course, we have seen, and bond strength is not necessarily proportional to paste strength, not proportional to paste strength, I will call it cement paste strength. It is not proportional to paste strength. So, that is one must understand. ITZ governs the concrete strength. ITZ governs the concrete strength, that is what we have seen. So, the bond is very, very important. Now, what governs this paste aggregate bond? Cement type is a factor, but there are other factors. So, let us see other factors. This bond is mostly mechanical, physical, and in very few cases can be chemical, but mostly it is mechanical and at best physical. Mechanical bond, you might have roughness of the surface of the aggregate, and paste might come in there, paste might simply come and sit there, paste might simply come and sit there, paste might simply come and sit there. So, it is mechanical bond, mechanical, you want to pull out, this is the paste. So, it could be simply mechanical bond sitting on the roughness of the aggregate. Physical, between the paste to paste is physical, paste to aggregate is not necessarily, not many times physical bond, but adhesive forces can exist, because one was in plastic state, other is solid, the aggregates are generally solid, paste was in plastic state. So, there could be some sort of physical bonding may occur, but largely it is mechanical bond. Chemical bonds are rare, and this occurs essentially in case of pozzolanic aggregate. So, we will just see that, okay, we will come back to that, sometime later on, that sometime it is chemical, largely when you have volcanic source, aggregate from volcanic source. We will come to that sometime later on. Now, water cement ratio affects the bond in a manner similar to that it does to the compressive strength of the paste. So, water cement ratio affects the bond strength in a similar manner like it does to the compressive strength, and we have discussed this in the last lecture, that ITZ properties, its porosity is a function of the water to cement ratio. Effect of surface roughness is evident in low water cement ratio, at very high water vanishes, at high water cement ratio it vanishes. Surface roughness is an important factor, surface roughness of the aggregate is an important factor, particularly at low water to cement ratio, because the bond is mechanical. So, therefore, surface roughness is very, very important, right, surface roughness of aggregate. So, if you see what is surface roughness of aggregate, I mean a honeycombed aggregate. If it is a polished surface, texture is polished, you can have textures, polished textures to rough texture, honeycomb structure, and so on and so forth. Textures of aggregates are also classified. So, if it is absolutely polished, glassy or polished texture, then the bond would be poor, while if it is rough, the bond would be better. It is nothing to do with the shape of the aggregate. Shape could be circular, spherical, and even you can have surface somewhat rough or honeycomb, depending upon type of aggregate. All right. So, roughness is very, very important. Now, testing this is not very easy, effect of roughness, but some test has been done. For example, bond is created between aggregate surface and the paste, and then try to find out through a pull out kind of a test, and some results are available. Typically, we will just show it in a kind of table. So, some results are available. Volcanic, as I said, the chemical bonding occurs when you have got volcanic extrusive rocks from volcanic eruption, and they can have better bond of strength due to lime silica reaction, because cement hydrates have got lime, that is what we have seen earlier, and this lime can react if the aggregate surface has got some sort of reactive silica. So, pozzolanic sort of similar to pozzolanic reaction this can occur, and some of the calcareous aggregate due to growth of calcium carbonate, calcium hydroxide solid solution may exhibit higher strength. So, because of solid solution of calcium carbonate, some calcareous aggregate and calcium hydroxide produced from the cement hydration solid solution can form. So, this may exhibit higher strength, but this is very rare, this is not very, these two are not very, chemical bonding is not very common. So, mostly it is mechanical, as I mentioned. Some aggregates exhibit chemical bonding, all right. Now, the cement aggregate bond arises from mechanical, physical or chemical bond. Surface rugosity or roughness plays a major role. Mechanical interlocking rather than chemical bonding, tackiness, this is a question of surface properties, tacky surface. So, the adhesive penetrates into the pores or holes and scratches of the substrate to bond. That is what I was saying. Supposing you have got a surface, like this with some holes here, surface with some holes here, some holes here, honeycombed aggregate surface, exaggerated, and the material goes inside this. So, it creates bond. So, adhesive, that is our aggregates, they will penetrate inside to the substrate and creates the bond. So, that is what I showed earlier diagram also, that is mostly mechanical. The roughness values, although small, are quite huge compared to the bond strength, bond length. So, roughness values, they can be small, but in absolute term, but large compared to bond length. So, bonds are order of nanometer, roughness could be order of millimeters, microns surely, but could be order of millimeter or microns surely. So, therefore, they are very large, and therefore, roughness is a major issue here. So, bond strength, bond length is very small. So, bonded material they penetrate into the roughness. Van der Waals bond can act on surface of dissimilar material, but this is not very major role. Aggregate paste bond is mechanical, and this is what the people studied related to roughness. So, roughness values in micron from central line. So, these are in 1.6 to 6.3 board or turned material, is milled material, you will have 1.6 to 6.3, lapped or polished material. So, polished material has got the least, ground material is something grinded material. So, milled board, but surface profile from average central line, these are the roughness values, but aggregate may have still larger values, aggregates may have still larger values. Now, how does 0.4 water cement ratio, I just mentioned earlier, 0.4 water cement ratio, the reduction in strength because of surface structure could be as low as 0.7, strength could be, as we said, it could be as much as 0.7, 70%, and it vanishes somewhere. So, if one looks at this roughness values, if one looks at 0.4 water cement ratio, a factor, it can be roughness, smooth to rough surface, smooth to rough surface. If you look at it, smooth surface may have strength 70% of that of rough surface. With 0.65 water cement ratio, same, it is 100%. So, variations, if you have 0.4 water cement ratio, strength reduction could be, the smooth surface can result in reduction in strength to as much as by 30%, while for 0.65 water cement ratio this does not have any effect. So, that is how the roughness affects, right. Now, what about aggregate properties itself? If you look at it, ordinary concrete strength versus water cement ratio, strength to water cement ratio varies. As water cement ratio increases, strength decreases. But if you come to some lightweight aggregate concrete which are weaker aggregate, they actually exhibit lower strength, especially when water cement ratio is reducing. And cracks can pass through the aggregate themselves, cracks can pass through the aggregate themselves, cracks can pass through the aggregate themselves, because weak aggregate. So, strength is usually governed by the weakest link. If the paste is weak and paste ITZ is weak, it will pass through ITZ, will not cause cracking of the aggregate, but it may start from ITZ in any case if it is the largest void, but as it initiates it might pass through the aggregate straight away if the aggregates are weak. For example, if you just breaks low strength bricks, something like 7.5 MPa or bricks or 10 MPa bricks and crush them and make aggregate out of them, particularly 7.5 or so bricks, and make concrete out of them, you will find that the strength of the concrete is low, even if your water cement ratio is relatively low, strength of the concrete is low and all the fractures planes are passing through the brick aggregate themselves, So, strength of the aggregate is an important issue, weaker aggregate exhibit lower strength, right. So, more so in low water cement ratio scenario. Modulus of elasticity affects the concrete fracture properties, that affects the strength, because we said that the modulus of elasticity of the pore free material, that governs the critical stress at which fractures would propagate spontaneously. So, fracture properties and thus affects the strength. So, therefore, modulus of elasticity of the aggregate is important, because modulus of elasticity will govern the pore free solids modulus of elasticity. The modulus of elasticity of the pore free concrete system is a function of the modulus of elasticity of the aggregate as well as pore free paste. So, if E of the concrete we just can write, it would be a function of E of the aggregate and E of the paste, no pore, pore free. So, if you look at this, porosity will bring it down. So, therefore, E of the aggregate has got a role. All fracture properties are controlled by modulus of elasticity of the aggregate, and therefore, this will play a role in strength of the concrete. High modulus obviously tend to give you higher strength. Aggregate with higher modulus shares more load at a given strain and relieves the paste. So, this is also an issue. For example, if you just consider this is my aggregate and this is my paste, and I am loading just as a simple model, I am loading it like that. So, under same deformation, so if the deformation occurs are same, under same deformation occurring is same, deformation is same. So, this has got low E, E is different, this is let us say E is higher, E AGG is higher than E P. So, E aggregate higher, it will actually stress P by proportions, it will depend upon of course, the proportions. So, the load shared would be P 1 plus P 2 and total load P, and P 1 would be related to same deformation. So, E epsilon into and same area, let us say volumes are same for the time being, then it would be simply P 1 will be equals to strain same into E into A, E A into epsilon. So, E aggregate into epsilon plus P 2 will be E paste into A into epsilon, both will have same deformation. So, whichever is higher will share more the load, if the area is same, just for the understanding part of it. So, higher modulus shares more load at a given strain and relieves the paste. So, paste will be loaded less, it can share more and it can relieve the paste. So, that is the idea, that is the idea, that is the idea, and size is important, because larger the aggregate size, for example, in this direction size is increasing, larger the aggregate size, right. So, size effect, larger the size, strength to water, compressive strength to water cement ratio, strength decreases. So, larger size means stress concentration around, same stress. Supposing I have got large size, the stress, same stress has to pass through it, same stress has to pass through it. So, this is lesser area. Now, you have got smaller sizes occupying same volume. So, surface area is more surface area, more surface area for smaller size. Thus, as the size of the aggregate increases, strength can reduce, as the size of the aggregate increases. So, more surface area for smaller size, for same stress, for same force, stress for larger size will be more, larger size would be more. So, therefore, because that's it would be more. So, therefore, size has got a role, larger the size, strength will be lower, right. So, this curve is lower, and it has been actually observed that MSA governs the strength. How does it govern the strength? MSA governs the strength. You see, it has got two kind of an effect. Larger the aggregate size, stress around the maximum size of the aggregate, larger the MSA, stress around the maximum size aggregate is going to be higher. But it has got a role in packing too. Larger the size, less paste would be required to fill it in. Now, strength could be lower there. So, what has been observed is that if you go on increasing MSA along this direction, for low cement content, strength increases as you increase the MSA, and then it does not increase further. Here the strength increases, becomes constant, and at high cement content strength increases and start decreasing. So, as you go on increase the MSA, as you go on increasing the MSA, your aggregate itself is also strong. Overall, there is an increase, but at higher cement content, actually this effect of stress concentration around the larger size aggregate starts dominating. Here the aggregate is paste is not very strong, low cement content, paste is not less, paste is less, and the maybe your in a lean concrete situation, paste is less. So, it is aggregate which dominates the strength. More the aggregate, larger the aggregate, maybe larger size of aggregate you can accommodate, strength increases, but as you increase it beyond a point, this point stress concentration around the aggregate starts dominating. So, MSA increasing, strength increases in the beginning, but here this is for high cement content situation. The strength increases, this axis is strength increases and then starts decreasing. So, what we find is that when you have got mass concrete, where paste is relatively low, overall strength itself is also low. So, there you can actually accommodate larger aggregate without compromising onto the strength, while you have got relatively higher strength concrete, structural grade of concrete. If you increase the MSA, strength starts reducing, because overall strength is higher, your paste content itself is higher, cement is more, cement is high, and the stress concentration around the aggregate starts affecting lowering down the strength, because strength is governed by the weakest link. So, this is the reason why you find that MSA for structural grade of concrete is mostly 20, sometimes 40. For mass concrete it is 75 mm or 150 mm. and for high strength concrete it might be 10 mm simply or 12.5. Very high strength system may not have at all the coarse aggregate itself, because uniformity is required, stress concentration around the aggregate is not desirable, non-uniform, one material to transition from one material to another material. So, it should be uniform material, as uniform as possible. Non-uniformity always results in stress concentration, because modulus of elasticity of the paste and aggregate will be different. So, therefore, there will be stress concentration around the aggregate system, and that is reduced, just lowered down, right. So, size of the MSA is important. Basically, presence of aggregate particle introduces stress concentration at interface. Volume of region of stress around aggregate increases with aggregate size, right. And in practice, lean concrete MSA is higher, lean concrete MSA is higher, lean concrete MSA is higher because of lower requirement of paste and water, thus water cement ratio can be reduced with higher MSA. You can have low water cement ratio, but higher MSA, paste should be less, paste should be less. For higher strength, stress concentration discontinuities and lowering of bond area dominates, and therefore, your MSA is limited to certain value, something like 20 or 40 for structural, as I mentioned. Concentration, quantity, how much is the aggregate quantity? Particle separate reduces if I have more aggregate, this is less aggregate, aggregate is paste is more. Another case, I have got more aggregate. So, the particle separation reduces, particle separate reduces, less fracture length for high concentration. So, if you have high concentration, the distance between two aggregates are small, high concentration, and therefore, fracture length is lower. That is what the idea is, but the other side of it is aggregate introduces discontinuity and stress concentration, and volume region of stress concentration overlaps as aggregate content increases, decreasing the average stress. The strength increases with aggregate, more secondary cracks with high concentration, that is also observed. So, because regions of stress concentration would tend to overlap, and therefore, actual area tends to becomes larger, and this causes more aggregate, tends to reduce down the effect somewhat, and strength increases. Well, normal strength concrete actually in very high strength concrete, paste content is in fact more to counteract the shrinkage effects. The shrinkage effects will also come in, as your paste is more or cement is more, there can be shrinkage effects. So, that might result in cracking of the whole thing. So, your aggregate system, more aggregate system, the shrinkage effects also will be relatively less. Generally accepted that strength increases with aggregate content in normal concrete, generally accepted that strength increases with aggregate content, because aggregate themselves are strong, quite often more more stronger than the paste itself. With increased aggregate content, capillary porosity may decrease. Also, average stress in the zone of stress concentration reduces. So, that is the idea, that is the idea. So, everything is stressed in a similar manner, and that is why as you increase the aggregate, strength increases in ordinary normal strength concrete. But where there is high strength concrete, you might have to have much higher paste content to ensure that there is a bulk shrinkage rather than shrinkage between the aggregates. We will come to that sometime later on. Strength is related to water content and porosity and cement, water to cement ratio, as we have seen, porosity and pore sizes. Now, this is water cement ratio governs the strength, that is what we have seen. Now, if you have air content, then you introduce more porosity. So, effective water cement ratio in fact would be increasing. Anyway, I can say that way. Finally, the role of water cement ratio, higher water cement ratio results in more porosity. Air entrainment also can introduce a pore and thus reduces the strength. So, you can think in terms of an effective water to cement ratio being increased. Well, we can now understand pretty well that actually we have been talking about that directly, that porosity water cement ratio causes increase in porosity and pore sizes, and therefore, there is a reduction in strength. Air entrainment, the pores are of course closed pores, they are closed pores, not interconnected, well distributed, but the sizes are also quite large, and they can introduce air entraining agent can introduce pores, closed pore systems, and they have a tendency to reduce down the strength. But we might sacrifice that strength if we are getting benefit in certain other properties, particularly durability, which we shall see later on. So, air entraining agent has also it can reduce the strength by about 5%. It can reduce the strength by about 5%. Compaction pores are very difficult to define. They can come because of the air void remaining. You have not compacted it properly. So, some air void remaining, we have seen that vibration can remove air voids, but supposing we have not done 100% vibration, there is no honeycomb as such, but the voids are remaining. Now, these air voids will also reduce down the strength. Therefore, proper compaction is absolutely essential in order to ensure that your strength attained strength is proper, That is what it is. So, effect of compaction. Now, you can see that this is fully compacted concrete. If you do a hand compaction, the strength might come down, especially with low water cement ratio, because workability, the consistency of the paste may not be high enough to compact it easily, or flow properties may not be good enough for compaction. And if you have vibrated concrete, of course, you can go further, but still poorly compacted concrete can show bad results, and this can happen in low paste content. So, this axis is actually your water to cement ratio, and this is your compressive strength. So, compressive strength versus water to cement ratio, normally the curve should have been like this, but if I have a poorly hand compacted concrete, I will get like this, poorly vibrated concrete, I will get like this, because there will be compaction pores coming in. So, compaction pores coming in results in this. Age, strength will vary with the age. For example, you have 1 day strength, 3 day strength, 28 day strength, and 1 year, and so on and so forth. So, as the age increases, strength increases, compressive strength increases, the strength versus water to cement ratio, this strength. So, strength versus water to cement ratio curves, they tend to go up with age, and we do understand this, because with age hydration will progress, resulting in lower porosity and pore sizes. So, strength should increase. So, strength shall increase. Now, this is a function, hydration itself is a function of course, water cement ratio, but as you can see, this effect should be, this effect is quite prominent in low water cement ratio, but even high water cement ratio is also fairly prominent. Low water cement ratio hydration possibility is actually more, but then of course, there is a range beyond which 0.4 we are talking of, 0.3 we are talking of. Beyond that, of course, hydration, full hydration is never possible, but does not matter. This is, we have discussed this sometime earlier, that full hydration is not possible beyond certain below certain water cement ratio, right, but does not matter. This the blocking or reduction of the porosity is most important aspect. So, as the age increases, porosity will reduce, pore sizes will be finer, refinement of the pore size would take place, and therefore, strength increases, and strength to water cement ratio curve tend to go higher, right. So, at 1 day variation is less, but if you look at the variation at 1 year from high water cement ratio to low water cement ratio, that is significantly high, significantly high. So, what are the factors those affect strength? If we look at it, first of all, type of cement has got a role. Let us say this is the paste, affecting strength of paste. We are looking at strength of paste. So, type of cement has got a role on paste strength at a given age, of course, age of the paste. So, paste age, type of cement, age, curing condition, because hydration will progress only if you have right kind of curing condition, and degree of hydration. This 3 will govern the degree of hydration, because you have a slow hardening cement. Say one thing is rapid hardening cement. Now, rapid hardening cement, which you have discussed right in the beginning earlier modules, rapid hardening cement would hydrate at a faster rate. Therefore, the type of cement at any given age, how much strength development occurs or degree of hydration is also a function of that. Degree of hydration will depend upon type of cement, while a pozzolanic cement or low heat cement, we know that degree of hydration will be lesser. So, so this degree of hydration will depend upon age, type of cement and curing condition. And if you have added admixtures, of course, they would govern that. If you have added admixtures, they would actually either retard or accelerate or whatever it is. So, they will also control, but this degree of hydration is also a function of water to cement ratio. As I mentioned, this is a function of water to cement ratio, and this degree of hydration and water cement ratio actually controls porosity, right, controls porosity. Now, admixtures, type of cement and all this actually controls the gel structure and composition. Now, I would like to add here the pore sizes also, pore sizes, it is not only the porosity, but the pore sizes, overall pore structure, the gel structure, everything is governed by this. So, this and the measurement during the moisture condition governs the paste. For example, dry specimen shows higher compressive strength, but wet specimen shows lower compressive strength. That is because when we will talk about the moisture condition sometime while doing testing. That is because some of the surface energy absorption of moisture would require, after that once the moisture is absorbed, you will require less surface energy to produce a fractured surface. So, some of the moisture it is surface tension properties. So, surface now earlier it was between solid and air, now it is between solid and water. So, the surface energy change occurs, and we know the friction between the particles would also become lesser, and therefore, the strength will be less. So, the moisture condition is also important. So, strength of the paste therefore, is governed by type of cement, age, curing condition and admixtures. Of course, the strength is governed by porosity and pore sizes, and which is governed by type of cement, age of the pores, curing condition, any admixtures that you are adding, degree of hydration is controlled by all of them, and they control the porosity. Also on water cement ratio, degree of hydration is controlled, as well as water cement ratio governs the porosity, and then gel and structure would depend upon all these factors, and finally, the moisture condition. All this actually governs the strength of paste. So, this is the strength of paste. This is the strength of paste, Now, strength of paste has a role in strength of concrete. So, now we are talking of concrete, strength of concrete. So, strength of paste has got a role in strength of concrete. So, it has got a role in strength of concrete. Now, just aggregate is the other one which governs the strength. So, what are the aggregate properties? First of all, basic quality of the aggregate in terms of its in terms of its particles, quality of aggregate in terms of particle size, its modulus of elasticity, right, and of course, the surface characteristics, that is roughness that we mentioned, chemical composition, because some chemical composition can give you higher bond, and its number, volume, this is volume, concentration here means volume, particle size, modulus of elasticity, this is all discussed, chemical composition and surface characteristics, overall quality of the aggregate in terms of its shapes and things like that, flaky shapes and so on, they have some effect on strength. Now, all this actually governs the paste aggregate bond together with the paste strength, paste aggregate bond, right. So, paste aggregate bond is controlled by the surface characteristic, chemical composition, quality, etc., but also controlled by paste strength. So, page strength is not the only one, this all controls actually the page aggregate bond. And then this together page strength, this together page aggregate bond together, and the page strength, also volume concentration of aggregates, that is particle size of aggregate and modulus of elasticity of aggregate, they themselves control the strength of concrete, because this is a phase, aggregate is a phase, bond is the other issue, aggregate itself is a phase. If it has got low modulus of elasticity or lower strength, cracks can pass through the aggregate itself. So, therefore, particle size, stress concentration, volume, all this governs actually strength of concrete together with the page strength and page aggregate bond. So, this is what we have discussed, and this diagram gives you the complete idea. And then of course, your production factor is important, which governs the strength of concrete. If you have not done compaction properly, strength of concrete may not be appropriate. So, that is the idea. These are the ones, all controls the properties of concrete. So, we looked into page strength and then into how page strength, what governs the page strength, and page strength itself governs the page aggregate bond and also the strength of the concrete, because in the concrete page is a phase, bond is also a phase, ITZ. So, this is what it is, but aggregate is also a phase. Therefore, aggregate properties also govern the strength of concrete. So, that is all governs the strength of concrete. Now, we can look into the tensile strength of concrete. So, main properties of concrete is main mechanical properties with which we are concerned is the compressive strength, but then sometime we are also interested in tensile strength of concrete. Let us see when we are interested in tensile strength of concrete. We rely mostly on its compressive strength, very little we rely on its tensile strength. However, tensile strength is important for shrinkage, shear, differential movement, etc., because they can result in cracking. So, unless you have right kind of tensile strength, it can result in cracking, because if you have restrained shrinkage, if something is trying to shorten and you are not allowing it, which can happen in structures. So, if you have restrained shrinkage, there will be tensile forces coming in, and it can result in, you may not apply directly the tensile force, may not expect the direct tensile load to be resisted by the concrete, but tensile strength coming because of the shrinkage. Shear is always complementary, as you know, flexural shear, there will be tension and compression. I mean, shear can be resolved into two components of tension and compression. Then any differential movement, some place has gone down, so, moved relative to the other, that results in internal stresses, and all this can result in cracking because of the low tensile strength. So, cracking occurs because separation of the particles, separation of the material, and that is because of the low tensile strength, all right, low tensile strength. Certain structures, for example, dam under earthquake excitation, pavement slabs and airfield runway are designed on the basis of either direct or flexural tensile strength. Water retaining structure, you do not want them to crack, because you do not want water to penetrate. So, therefore, there also tensile strength becomes important. Pavement slabs, tensile strengths are important, and earthquakes, dams under earthquake excitation. These are some places where we rely on the direct tensile strength or flexural strength of concrete. So, tensile strength need to be known, but fortunately it can be related to the compressive strength. It need to be known, but fortunately we can relate it to the compressive strength. Okay. Let us see the failure envelope of concrete under biaxial situation. That means, you have applied, there is one direction and this is another direction, biaxial situation. So, this side is tension, this is compression, this is tension, this is compression. So, P is applied here, P minus is compression. So, that is the failure envelope of concrete, this is the failure envelope of concrete. That means, this is the boundary. If you have tension alone in one direction, more than this it will fail, even if this is 0, there is no force on the other direction, tensile force. So, it can withstand this much K as its tensile strength either direction individually, uniaxial. And of course, biaxial situation it can, biaxial compression it can withstand lot more. So, it can withstand, if I look at compression along only this direction, there is no force along this direction, it can withstand around 8 K. Similarly, K here, 8 K there, K here and 8 K there. So, but combinations, if you look at it, this is the situation. For example, in this case it is 3 K, right, is a compression, less than a K in tension, slightly less than K in tension in one direction, okay, tension in one direction, and compression in the other direction is 3 K. So, it can withstand that much, whereas it can withstand here K and K tension in both the directions, that sort of thing. So, this is the failure envelope. So, what we see is compressive strength is around 8 times of tensile strength, and therefore, there can be a relationship can exist between the tensile uniaxial tensile strength and uniaxial compressive strength, you know. So, one can look into this. Now, we measure tensile strength in two different ways actually. We will discuss this in the next lecture. We actually measure them in two different ways. It is of course difficult to measure direct tensile strength, although there are people now, there are some attempts to do it, but most commonly we measure by specific method called split tension method, split cylinder method, and this is splitting. So, which gives you some indication of the direct tensile strength. And another way is to measure the tensile strength under bending load, okay, where because bending induces tension, as we know, in a simply supported system at the bottom fiber with a load at the top, the bottom fiber is under tension. So, the concrete we can test in that manner, and that is flexural tensile strength, that usually is higher, and that can be related to compressive strength, you know, dry and wet condition. We can see that dry and wet condition, moisture condition also affects the strength, as you have seen. So, when we do you know, when we look at a lecture in method of test methods, then we will come back to split tension test and flexural test, but we find that the strength in varies, compressive strength varies, I mean tensile strength varies with the compressive strength, both split as well as flexural. Wet and dry condition, we will discuss this sometime later on, because dry condition you can see the strength is low, wet condition strength is higher, that is for a specific reason of shrinkage actually. We will come to that sometime, while split tension the difference is very little. So, wet and dry the variation is very little. So, but what one can see is that one can relate the cube compressive strength and tensile strength, and people have done that. So, basically compressive failure is also a tensile failure, that is what we have seen in the other lecture, because it is the failure occurs in the transverse direction, right. Failure occurs in the transverse tension in transverse direction when applying compressive, uniaxial compression failure occurs because of the transverse, failure occurs because of this, cracks can occur because of this, and therefore, they are related. So, compressive strength versus flexural strength, one can relate it in this manner, one can get curves of this kind, one can get curves of this kind, generally lot of scatter, but variation would be something of this kind. And similarly, if you measure by split tension, you get it for split tension, you get it something like this. This is the flexural test, we will talk about that sometime later. So, generally with various size of aggregate. So, you can see typically it will vary in this manner, some sort of a variation is available, and people have tried to empirically relate the tensile strength with this is split, this is flexure, relate it with the compressive strength. Some equations have been developed, and several factors of course, will affect this relationship, as we have seen in the previous curve. As we see in the previous curve, the type of aggregate, the scatters is because of the type of aggregate, MSA values and maximum MSA values, and there could be other cases such as moisture condition, etc., many factors would affect this. So, several factors affect the relationship between compressive and tensile strength of aggregate, its aggregate type, age, curing, water cement ratio, but through empirical formula one can relate them. One can relate them through empirical formula. For example, F t is equals to K F c to the power n, where F is strength, K and n are constants. So, n would depend upon what type of strength you were relating, right, and K would also depend upon what type of strength you are relating. For example, for flexural strength, K can be different, N can be different. For split cylinder test, K can be different, N can be different. Okay. So, IS 456 of course, it says K equals to 0.7 and N is equals to 0.5 for fractional strength. So, F T is given as 0.7 under root F C K is characteristic strength, F C K characteristic, not F C, but F C K characteristic strength. So, this is largely for design purposes, a little bit of conservative value it would be. So, design purposes, this is what gives you Indian standard code. All other codes have similar sort of formulae available. So, then what we have looked into so far? We have looked into the role of paste in the compressive strength. We looked into the role of ITZ last time, but then we have right now we have looked into a little bit more the bond strength. We have looked into bond strength. We have looked into bond strength in the context of aggregate. We have looked this into context of aggregate. And what we have seen that paste strength, aggregate properties and paste aggregate bond all govern the strength of concrete. Paste strength itself is controlled by type of cement, type of admixture if you are using, and water to cement ratio, degree of water to cement ratio as well as age. Both this actually controls the degree of hydration as well. So, one can get an idea what governs paste strength. So far we have looked into, but paste aggregate bond is governed by the aggregate property as well. Last lecture we discussed about paste, strength of paste, water cement ratio and those factors, but the bond between aggregate and paste is governed also by aggregate properties like surface roughness, texture essentially, and some cases there could be chemical bonding, that is what we have seen. And then aggregate properties, paste properties and paste aggregate bond, all of them together with the production factor governs the strength of the concrete. Then we have lastly looked into the strength of tensile strength. We have looked into the tensile strength of concrete, and we have said that this can be measured in two ways, which we shall see later on, test methods, as we will see in the next lecture. But however, both this can be related to the compressive strength, because after all compressive failure of uniaxial compression failure of concrete is under transverse tension only. So, there has to be some sort of relationship tensile and compressive strength. It could be 8 times, compressive strength could be 8 times, that we have seen from the failure we have seen from the failure envelope. So, therefore, one can get a relationship. Typically empirical relationship has been established, large number of factors govern this relationship, and they are of the kind of F t is equals to F some constant into F c to the power n. Different code uses different values of n and k, and also it might differ depending upon type of the cementitious material you are using and so on and so forth, but code gives you a conservative value, and IS code of course gives you a value of F t is equals to 0.7 under root F c k, where F c k is a characteristic strength. So, I think we do this would conclude our this lecture and of lecture of 6th module. Next class we will look into the test factors which governs the strength of the concrete. Test factors, both tensile compressive as well as tensile. Thank you very much.